In this video, we'll look at the structure and operation of CMOS comparators. Stated simply, the function of a comparator is to produce a binary output that is either a high or low voltage, depending only on the sign of a differential input. The output of the comparator may be differential or single-ended, in which case its output is interpreted with respect to ground as usual. So such functionality, in fact, is provided by any amplifier with very large gain. So one might wonder, why not simply use an op-amp circuit? Without feedback, a typical op-amp has a very high DC gain. So the output would likely saturate, depending only on the polarity of the input applied, even if the input is relatively small. The problem is op-amps are typically compensated to have good closed-loop stability, and therefore they typically have a slow dominant pole. So when you operate the op-amp open loop like this, the settling time constant at the output, tau here, would be inversely proportional to the dominant pole frequency, which is likely very low. So for an example, an amplifier with an open loop response like this would have a settling time constant of about 0.16 milliseconds. So in summary, op-amps are very slow when operated open loop, and that limits their usefulness as a comparator. It is possible to speed up the operation of an op-amp for use as a comparator. Now, in order to do this, let's look at the two-stage op-amp shown here. And you see the Miller compensation network comprised of transistor Q1 operated in triode and serving as a lead compensation resistor, and compensation capacitor CC. Now, since we're operating the op-amp without feedback when we're using it as a comparator, there's no need for this compensation network when operating it open loop. So a clock signal, phi1, can be applied to the gate of transistor Q1. This would periodically disconnect the compensation network, turning off Q1. Doing so would increase the dominant pole frequency associated with this node and would allow the op-amp output to settle much more quickly. Now you might have to turn the transistor Q1 back on periodically to reestablish a reasonable operating point. So the signal at the gate of Q1 is likely a clock that is alternating between a comparison phase and a reset phase. Using a technique like this can certainly speed up the settling time of an op-amp, perhaps by an order of magnitude or two. But there are other techniques that allow for much faster comparators in CMOS. Most comparators in modern CMOS technologies are dynamic comparators, and an example of one is shown here. To understand its operation, consider the signal labeled V-latch. And consider what happens as it alternates between a high and low voltage level. So first, let's consider what happens when it's down to ground. In that situation, these transistors will be turned on, and these transistors will be turned off. As a result, the input signal is disconnected effectively from the output nodes, and the PMOS pull-up transistors pull these two nodes both up to the supply voltage, which let's call it VDD. These two nodes both being up high, we see that the outputs of the latch, V out plus and minus, will be the outputs of the inverters, and so they'll be also both low. So this is a reset phase. Effectively, the internal nodes of the latch are both pulled up to VDD, the outputs are pulled down, and it's a starting point from which to understand the dynamic operation of the latch. Next, let's think about what happens when the signal V latch goes high. Oops, let's call it a binary 1, but really it's a high voltage level that would ideally be equal to VDD, the supply voltage. So in that circumstance, these two transistors would turn off, and these two transistors would turn on and triode and serve as closed switches. Now you'll notice with those transistors on, these two transistors here form an inverter with this node here as its input. And we've got another inverter formed by these two transistors, which have the output of the first inverter as its input. So essentially, you have two back-to-back inverters, as shown in the schematic at the bottom. Now these intermediate nodes here, Vx and Vy, are also being acted on by the input pair transistors circled here. So these are common source transistors whose gates are connected to an amplified differential input. So when Latch goes high, we see that a small differential current is injected onto these two nodes, which are both starting up at VDD. And depending on which side of the differential input is at a higher voltage, we'll see that one of these two nodes will be pulled down towards ground faster. Now, at some point, the differential signal that arises between Vx and Vy will activate a positive feedback loop formed by these two inverters, back-to-back inverters. So what may initially be a very small differential voltage between Vx and Vy will grow because it'll get amplified by the positive feedback action of these two latches until eventually the two voltages saturate, one at VDD and one near ground. And then at the output, we just see a sort of cleaned up version of that where the outputs and the inverters transition a little bit more quickly from ground, from VDD to ground. So ultimately resulting in a differential logic signal whose polarity depends on the sign of the applied differential input voltage. So there's several advantages of comparators like this. You can realize by taking advantage of the positive feedback, you can realize a very large gain, and there's actually potentially much less power consumption than in an op-amp circuit. You'll notice here there's no DC bias currents flowing. So the only current that's flowing is a transient current that's being used to periodically charge and discharge some of these internal nodes. So we've just got dynamic power whose value is proportional really to the frequency with which we toggle the latch between reset and latching mode. So for a given clock frequency, you're going to consume a lot less power this way. Dynamic comparators can also operate at a lot higher frequency. The exponential growth of the positive feedback allows for very fast settling at the output, and we'll see a description of that in the next couple slides. But the downsides are that generally such amplifiers may have less accuracy and more clock kickback than op-amp-based comparators. So this is because the large voltage transients that arise on these internal nodes Vx and Vy can be coupled back to the inputs through the gate capacitance of these input transistors and cause spikes of charge or current flow and therefore ripples in the voltage at the input to the latch. Now that's why you see pictured here a preamplifier connected between the input and the positive regenerative stage here. The preamplifier can help ameliorate some of the negative aspects of the dynamic comparator and improve its performance by having a little bit of gain at the front end and providing a sort of extra layer of shielding from any kickback. The preamplifier here need not be complicated. It's typically a simple differential amplifier with a modest gain, say a gain anywhere from 1 to 5 or so volts per volt. And because the gain requirements are not too severe, it can be operated at relatively high speed. So this is just one example of a dynamic comparator circuit. There are many others, but they generally all rely on this premise that by using positive feedback, we can resolve a large differential output from a relatively small initial differential input. And so the key point of dynamic comparators is that they're periodically reset, and then a positive feedback loop is activated to generate the output. So focusing on the operation of the dynamic comparator when it's latching, again, the basic core of the circuit will be some sort of positive feedback loop like this. Here, quite often, it's back-to-back inverters, but sometimes there'll be slight variations on this. In any case, the regeneration phase, as we'll call it, begins with 0 differential voltage between these two nodes, Vx and Vy, and then a slowly growing differential voltage appears between them, with the polarity of that differential voltage depending on the polarity of an applied input. Now that differential voltage will grow slowly at first until such time as the differential currents flowing into these two nodes due to the positive feedback network will start taking over, will become dominant. At that point, the difference between Vx and Vy will start growing faster due to the positive feedback loop. And in fact, will grow exponentially, as we'll show on the next slide, causing those two voltages to diverge. So when looking at simulations of such circuits, you can usually clearly identify these two different portions of the waveforms on Vx and Vy. Now there's something intuitively wrong about the cartoon shown here. It suggests that the positive feedback causes the voltages Vx and Vy to diverge indefinitely due to this exponential growth, but clearly at some point the finite supply voltages of the positive feedback amplifiers, in this case inverters, will limit the voltage that can appear there. So for example, these voltages may saturate around VDD and ground. At that point, we've got our binary differential output with a polarity that depends on the original differential voltage that was applied. So to understand the exponential growth during the regeneration phase of a dynamic comparator, we can take this positive feedback loop formed by back-to-back inverters and come up with a small signal model for it. So in this small signal model, we model each inverter as a transconductance, because we know that if we're got the inverters biased so that both transistors are in active mode, then we'll see both of their GMs drawing a current away from the output of the inverter. And that's what's represented by these voltage dependent current source, the small signal. They are the small signal, some of the small signal transconductances of the two constituent transistors for each inverter. And they're drawing a small signal current that depends on the input voltage. You've got the positive feedback formed because the output of one inverter drives the transconductance of the other inverter, and vice versa. Well, as shown here on the right, you can write a nodal equation for the voltage at Vx and Vy, where we represent the current through the capacitor as CL, representing the load cap on each of Vx and Vy, times the time rate of change of the voltage across that capacitance. So just to be clear, we've got the capacitors CL on each of these nodes, representing all the capacitances on those nodes. And there may be just parasitic gate source capacitances. Now the result of that analysis reveals two coupled first order differential equations here. But we can combine and simplify these two differential equations into a single differential equation by rewriting them in terms of delta V, differential output between Vx and Vy. In doing so, if we call this equation 1, this equation 2, we take the difference between the two equations, you end up with something like this. So now you've got a single first order differential equation in terms of delta V that has an exponential solution shown here. Now AV in this model, you'll note, is the DC small signal gain of each inverter, because at DC the capacitor CL are open circuits, so we simply have a gain of AV over RL times RL. So AV again is the small signal voltage gain of each inverter stage. So you'll notice from the solution to the differential equation shown in the bottom right here that as long as AV is greater than 1, that is, as long as each inverter has a small signal gain greater than 1, then the exponent in the solution here is positive, which means that delta V grows exponentially in time. The time constant tau in the solution is simply the time constant associated with each of the nodes Vx and Vy. That is, tau is the product RL-CL. So in summary, once the voltages at Vx and Vy reach a bias point that puts the inverters in a position where all transistors are in active mode, then certainly for any reasonable inverters, you're going to have a small signal gain greater than 1. And at that point, you've got the positive feedback loop formed, activated, and the differential voltage delta V that appears at that point in time. Let's call that initial differential voltage delta V naught. That'll serve as an initial operating point, and from there, the differential voltage will explode exponentially with a time constant given by RL-CL at each node. So a fast latch will want to have a large delta V naught formed by the time the back-to-back inverters get activated. So that kind of gives the regenerative pair a kind of head start in the exponential growth, and we'll want a large gain from the back-to-back inverters that will help speed up the settling at the output. And then finally, a small time constant associated with each of the nodes will also speed up the settling time at the output of the latch. And so again, this is just a generic picture of two back-to-back inverters, but if you examine them closely enough, practically all dynamic comparators will have a positive feedback core that can be cast into a model like this, and whose settling time therefore depends on the similar factors. Here are two examples of dynamic regenerative comparators that are popular in CMOS technology. They're both making use of the basic principles that we've described so far. On the left, we see the so-called strong arm latch, so named because of the microprocessor in which it was first applied. You'll notice here in red, I'm circling the regenerative positive feedback core, again consisting of two back-to-back inverters driving and connected between the nodes VO plus and VO minus. You'll also notice these pull-up transistors, PMOS devices circled in blue, which when the clock signal goes low, turn on and reset these nodes here, the output nodes and these internal nodes, by pulling them up to the supply voltage VDD. Then, when the clock signal goes high, activating the latch, these pull-up transistors are turned off, in a sense releasing the internal nodes of the regenerative comparator, and this bottom transistor here turns on, thereby allowing the differential current provided by the differential input pair driven by VI plus and minus, allowing that differential current to flow into the output nodes of the comparator. They'll both start being pulled down from VDD, but one will be pulled down faster depending on the polarity of the input voltage. And then at some point when the common mode at the output drops low enough, the two back-to-back inverters will enter their active mode and the positive feedback differential currents will take over and cause the regeneration and saturation of the output. Shown on the right is a more recently developed comparator that is generally referred to as the double tail latch. And it's referred to because there's really two series stages in this latch. In fact, the way I like to think of the operation of this latch is simply that this first stage here is essentially a preamplifier. It's just a funny sort of a preamplifier that's periodically reset. When clock goes low, these nodes are pulled high by the pull-up PMOS transistors connected above them. And then when clock goes high, these transistors are turned off, those nodes are released, and these nodes start dropping towards ground, but one will drop faster, creating a differential input at these internal nodes here. So the regenerative core here is, again, a couple of back-to-back inverters identified here in red, and they're being driven by a differential current generated by these input transistors here that have as at their gates the output of the preceding preamplifier stage. They sort of initiate the positive feedback loop, and then the back-to-back inverters take over and perform the regeneration. And again, all this happens when the clock signal goes high. In fact, there's an important error here in these slides. This signal here is actually clock bar. So when clock goes high, the preamplifier is activated and the clock bar signal goes low, activating the regenerative pair. So this double tail latch has this sort of built-in preamplifier circled there in yellow, and that is an additional stage, just like a preamplifier, shielding kickback from the input. You'll also notice that the regenerative core, circled in red there, really just has one transistor stacked on top of it, and that's the clock transistor. When it's turned on, it enters triode strongly and has a relatively small VDS across it. So whereas if you compare that with the comparator circuit on the left and the comparator circuit presented earlier in the slides, you'll notice those comparators have more transistors stacked on top of each other. There's 4 transistors stacked in the strong arm latch. So because there's fewer transistors stacked on top of each other, this double tail latch is generally well suited to low supply voltages where there's not much headroom to provide a strong overdrive voltage to the transistors. Now the outputs of the dynamic comparators that we've discussed so far accept as inputs differential voltage VI and a clock. And as the clock alternates between high and low, the latch alternates between a reset stage and a regeneration stage. So if we label these voltages VO plus and minus, we expect them to look something like this. In reset, both voltages are reset to the same node voltage. In some of the examples we showed, it was reset to VDD. So VO plus would go up to VDD, and so would VO minus. Let's use a different color for VO minus. Green. Then we enter a regeneration phase when the clock edge arrives. And we've seen that at this point, the two node voltages, if they're reset high, will start declining, one faster than the other, depending on the polarity of the input. And then, at some point, positive feedback takes over and the voltages will settle to their final decision values. One will go high and one will go low. And then we'll re-enter the reset phase. One signal will already be high and the other one gets pulled up high. So these are the kind of funny waveforms we see at the output of the latch here. But what we'd like to really see ultimately is a sort of nice clean decision formed at the output of our latch. For every clock edge we expect to see, either 1 or 0. And maybe we've got a differential output, so we have something like this. So to get rid of this periodically resetting part of the waveform, we need to introduce a second stage here, an RS latch. And this will do what we want. Logically, one way to make an RS latch is as shown here. The truth table here would be, the key point is that when both R and S are high, the output of the RS latch is held. So that will sustain the outputs of the regenerative comparator during its reset phase, so that whatever the subsequent circuit is connected to the output of the RS latch won't really see the reset phase. The output will simply go from one decision to the next. Then when we get a 1, 0, the latch will be reset low. When we get a 0, 1, the latch will be reset high. And for an RS latch like this, we would avoid the state when both outputs are low. But you see, that's perfect for the output of our regenerative comparator. If it's operating properly, we should really never see both outputs of the regenerative comparator go low. Now, you can realize an RS latch simply out of CMOS gates using the logic diagram circled here in black. There are alternative realizations that are a little faster, and so one example is shown here, taken from a paper, but you'll notice the functionality is the same. The two inputs here that are labeled A and B are actually R and S. And they're connected together. And you'll notice, let's consider first the example where A goes high and B goes low. So in such a case, this node is pulled down to ground. That activates this transistor over here. That pulls this node up to VDD, logical 1. Doing so turns this transistor off. It also turns this transistor off. Remember that A is 1, so we get out P and pulled down to ground. This transistor is also on because, again, the node here is pulled down to ground. And again, B is 0. So this transistor, these two transistors here are off. As a result, out N gets pulled up to 1. So when A goes high, out P goes down to 0. Clearly, A is the reset input. And we could do the alternative analysis here. And you would see that when B is high and A is low, the latch is set, the RS latch is set to a high state. So B is the set input. So that's just one example of an RS latch, but there are several alternative realizations of this. This one is relatively low transistor count. A key point here in the in considering how the performance of the RS latch affects that of the overall comparator is to recognize that if the RS latch is currently in a given state, let's say it's in the state we identified here, where in the schematic where out P is 0. Now, then we've got this transistor over here on. If we now change the state so that the set input goes high, let's say now things change so that B becomes 1 and A becomes 0. Well, now this transistor turns on, but initially at least, even though this transistor is now off, this node here is kind of floating temporarily, and it'll still be at its low logic level, which means that the pull-up transistor here will still be on. So you'll temporarily have a situation where these two transistors are sort of fighting each other, okay, to determine whether this node here is high or low. So clearly, this transistor has to be strong enough, that is, its W over L ratio has to be large enough to overpower the pull-up PMOS transistor. And during this brief interval of time when both transistors are on, there'll be a direct flow of current from VDD down to ground that can increase power consumption. Right? So it's not purely dynamic power being consumed here. Not all the current being drawn from VDD is being used to just charge and discharge capacitances on various nodes of the circuit. There's this kind of temporary current that flows directly from VDD to ground. It's just sort of wasted current. And that current can dominate the power consumption. So this transistor here has to be strong enough to overpower, and then the pull-up transistor, and then if it is, then the latch will flip. It'll pull this node all the way down to ground, and that'll initiate, that'll turn these pull-up transistors here on. That'll pull this node up to VDD. That'll then turn off these transistors, and then in steady state, there's no static power consumption. But again, temporarily, as the latch is transitioning, there's this additional flow of current. Moreover, the latch won't flip for very small differential inputs applied between A and B. So the input applied to the latch here also has to be large enough to flip the state of the RS latch. So depending on the relative sizing of the NMOS and PMOS transistors here, the RS latch will, may trip at different points and with different delays. So in summary, the overall architecture of our CMOS dynamic comparator is likely to look something like this. An input may be applied to a preamp that helps mitigate kickback of the clock into the input circuits. Um, we saw the examples where this preamp was a sort of dynamic amplifier, uh, but it can also be a simple resistively loaded differential pair with a modest gain. The second stage here is the regenerative positive feedback part of the latch. Often there's a combination of back-to-back inverters that's being periodically activated and reset by a clock signal. And then finally, you've got an RS latch that's being used to make the outputs nice and clean so that you don't see the reset phase at the output of the overall comparator. So this is a typical architecture. Obviously, there's variations on this theme. Uh, for example, sometimes you want to compare the input signal not to 0, but to some other reference level. So a reference signal may be applied, it may be applied either directly in the positive feedback latch by sort of applying a skew to that positive feedback, giving one side a bit of an advantage over the other. That's one way to create a kind of offset in the latch intentionally, and thereby cause the latch to only trip when the input exceeds a certain threshold. Or the reference can be applied right in the preamp, so the input is essentially subtracted from a reference voltage, and the difference between those two is then applied to the positive feedback latch. So that's one possible modification of this architecture, but you see that the overall result is a clock input, an input here being compared to some reference level, and then a binary output that can be in one of two states, depending on the polarity of the input upon arrival of a specified clock edge.